couple of points I want to make though. So these software packages were really designed for individual level models of disease transmission. So in the package, when we're simulating from the model, or when we're fitting the model, we're inherently assuming that individuals have their own transmission rate, or we call it a susceptibility rate, but it's an individualized transmission rate that varies between all of, or potentially varies between all of the population based on covariates, you know, spatial distance through a network, all that sort of thing. Now, what I'm going to do today is I'm going to force them to simulate from and carry out inference for these homogeneous mixing models. But because they're individual level, the underlying assumption is that we have an individual level model. It does it in a really computationally inefficient way. Waleed is actually working on implementing the SIR models in a much more efficient way right now. I've seen changes to the Dropbox folder, so I know stuff's going on. So hopefully in a week or two, you'll be able to use this software package to fit the SIR type models and the SINR models I'm going to talk about later in a much more computationally efficient way, right? But so for today, we're going to do it on real toy problems because the computation is not efficient. So that's one thing I wanted to make a note of. The second thing I wanted to talk, oh, and I should say what the two vignettes we'll talk about is how to use these software packages for spatial models and contact network based models and that sort of thing. So if you're interested in that, please take a look, and I will try to talk a little bit about that at the end if we have time. Okay, second thing. So far we've considered a deterministic ODE setup. We started with the SIR. We put a bit of structure on there. We talked about the sex stratified model and the age stratified model. I'm now going to go back to the SIR model to sort of illustrate the ideas here. But I'm going to change from having that frequency dependent model where, you know, the S, I, and R are the proportions of individuals at time t, so they sum to 1 at any point in time. I'm going to change to a density dependent model, so that now the S, the I, and the R will be the number, density dependent. There'll be the number of individuals in each compartment, so they're now going to sum to n, right? I've put these slides in the wrong order, but this is not strictly necessary. Like I say, for the closed population, there's really no difference between the model except the scaling. But the software package, being individual level based, thinks in terms, well, it doesn't think, but it's set up in terms of individuals. And also so is our inferential framework, right? It's built around what happens to individuals rather than proportions. But like I say, it's really just a matter of scaling. And I would argue that actually this is a more natural way to think of it anyway. It's the way I normally would think of it. Okay, so we can write a stochastic version of our ODE SIR model. So that's the model I'm talking about there, using the following probability equations, right? So we think about the probability of an infection occurring in a very small time interval from t up to t plus dt. Okay, so that, if we're prepared to make a linear assumption or a linear approximation, would just be beta times s times I, but of course, times the width of the interval. But of course, we've also got, it's not linear, so we've got these higher order things going on as well, right? So there's an approximation depending on how small that dt really is. We can think about it that way, and then the probability of a removal occurring in the population in this small time interval is just given by gamma, IT, and then all the higher order stuff. Okay, so with that in mind, conceptually, it's quite easy to think about simulating in discrete time, right? Using essentially a time varying, well, binomials really, but Bernoulli, right? This is describing the probability of those things, but we could simulate in discrete time quite easily. We're not going to do that. We're going to stay in continuous time, which in some ways makes things a little bit more complicated, but we're sticking with the actual model. And when we're working in continuous time, we're generally assuming exponentially distributed inter-event times. Okay, so the event here refers to either an infection occurring or a removal occurring. And so the times between, you know, two infections, or an infection and a removal, and a removal and a removal, whatever it is, follow some exponential distribution. Okay. Now, in that framework, and this actually follows from, if you go back to these models, go back to Keeling et al. Keeling and Rahani. They build the models up from first principles, and that actually leads to this exponential inter-event times, because there's an underlying Poisson process in the stochastic version. But anyway, we could, let's stop going off on tangents. We're assuming exponentially distributed inter-event times. So we can simulate from that model using something called Gillespie's algorithm, which if you've done a course in stochastic processes, you may have come across. So the original citation there from 1977, you can see, and you can take a look at that. The algorithm is actually given there in the context of chemical reactions and simulating chemical reactions. And I find it quite hard going, but there's a really nice explanation of it, probably in more places as well. But I go back to Alex Cook's thesis. So Alex Cook and I overlapped a little bit at Cambridge back in the around 2005, 2006. And his PhD is still up online. And he gives a really nice summation or explanation of how the Gillespie algorithm works in the context of disease modeling. And I'm going to summarize that here. So the basic idea behind Gillespie's algorithm is that you've got events of various type, okay, 1 to n. In our case, n is 2. Right, because we've got infections. In the SIR model, we have infections and we have removals. And those events have some rate that determines how often or how frequently they occur. Okay, so we have a phi 1 and a phi 2. Or shouldn't write plus, should I? Okay. So it turns out you can show quite easily that the waiting time between successive events of any type, so ignoring whether it's an infection or removal, the waiting time is given by an exponential distribution with a rate parameter, which is the sum of the component rates here. Okay, so I can simulate at any given time from that exponential to tell me when the next event will occur. Okay, and then in a second step, I can determine which type of event we have just by sampling from the weights. Okay, so I take the phi 1, oops, that should be a highlighter, my phi 1 normalized by the sum of phi 1 plus phi 2, and phi 2 normalized by phi 1 plus phi 2. Okay, so we can do it in two steps. Okay, and this is much more efficient, you know, than simulating the infection time for every next event and then taking the minimum, right, which is computationally much nastier. So we can use this framework to basically simulate the next event, when it occurs, what type it is, and of course, whenever an event occurs, whether it's an infection or removal, the rates will change. right? So the rates for my two events are given by our model before. The infection rate is beta S times I. The removal rate is gamma times I. And of course, if I've just simulated a new infection, then that will change IT and ST. So these two rates will change. And if I've just simulated a removal, there'll be one fewer infectious individuals. So these two rates will change again. So we simulate our event time, decide what the event is, update the event rates, and simulate the next event. Okay, so it's really simple algorithm, and it's reasonably efficient. And if you have lots and lots of different types of events, so more than just two, there are more efficient versions of the Gillespie algorithm as well out there. Okay, that's probably a good time to ask if there are any questions.
At this point, Rob, no. Thank you.
Okay. So what I'll show you now is how to do that process. So that was sort of describing what's going on under the hood. How to do that process using our continuous time EPI-LM package, right? Remembering that really this is trying to simulate from an individual level model. But of course, the homogeneous model is just a special case of that, right? It's an individual level model where there are no covariates, so everybody has the same transmission rate. Okay, so assuming you've installed the EPI-LM CT package, we call the library for R, and then the way that we force the package to do this at the moment, like I say, we should have an efficient function for doing this in a couple of weeks, hopefully. But the way we do it at the moment is that I assume my disease is going to travel through some network. Okay, so usually, you know, I might have a network that looks like this sort of thing, where some individuals are connected and some are not connected, right? Well, to simulate a homogeneous mixing population, what I have to do, and I've drawn too many individuals now, I'm going to erase that. What we're basically going to do is assume a saturated network. So everybody is connected to everybody else. Okay. And if I have another individual, they would have a link with everybody else. Okay, so the disease is actually going through a network, but it's saturated. Right? Everybody has, every edge, possible edge exists in this network. So the first command here, the contact net, is simulating that network. I have a random network as opposed to, say, a spatial one where edges closer in space are more likely to exist. I've got 500 individuals in this simulation that I'm going to run. So that's what the num ID is. And the beta here is not the beta that we've used previously for the transmission rate, or transmission rate, yeah. It's the probability that an edge between the node and the contact network will exist. Okay, so I've set that equal to 1. So every edge will exist in the network, okay? The command that actually generates my output from my now stochastic SIR model is called datagen, and I'm storing that in an object called epi. Okay, so a few things here. So I set my type of model to SIR. Okay, the kernel type that's really describing how people are connected. So that can be spatial, or it can be network, or it can be a mix of both. In this case, it's just network. Okay. If for a network model, I have to tell it what the network is, and that's what I just defined or generated up here, a saturated network. The sus par is really the beta in my SIR model. Okay, so I have a transmission rate of 0.01 here. And the infectious periods are generated stochastically from a gamma distribution. So we're thinking about the infectious periods in terms of the actual period rather than the rate to start with. So these are the parameters of my gamma here. So I'm simulating my infectious periods from a gamma 1, gamma 1, comma 1, or exponential with rate 1, which is nice and simple, obviously. Okay, and then finally we have a plot function. Okay, so if I run that code, what I will see is this. Well, let's ignore that one for now. I'll just stick to the top two. So you can see the epidemic curve in terms of the infection times. Okay, so I have the density on the y-axis rather than the number infected. But you can see we get this sort of similar shaped curve as we saw before, although this is quite a strong epidemic. So it's quite pointed, right? It's taking off and disappearing. Or we have a fast deletion of susceptibles there. So everything's sort of over by about time step 5. But you will see, of course, that this is now not a nice smooth line. It's got little wiggles in, which is most apparent at the end because it's now stochastic. Okay. I then got a second epidemic curve here, which is the removal times. So this is the time at which individuals are being removed. If you look, you'll see that the peak of my infection times is around 1. I think it's just after. And the peak of the removal times is around 2, which of course we expect because our infectious periods came from an exponential distribution with mean 1, rate 1. Okay, so that's what we get. The key difference here is it's stochastic, so we will get different realizations of this curve every time we run it. Okay, and just to show you, so the epi object, I go back over here, which is where I put my simulated epidemic. That contains all sorts of things like the network and any covariates I have, which actually I should say, so I forgot. So this part here, I'm basically saying there are no covariates. I could set this to be a vector, set it up with different covariates. So that option allows for individual level covariates, but we didn't want them here. But all that sort of stuff's stored in the epi object. One component of that is epidat, which shows you the infection times, the infectious periods, and then the removal times of each of my individuals. Okay, these are ordered. Okay, so you can see the infection times occurring. You can see the stochasticity in the infectious periods now. The ID over here comes from the fact that this is an individual level model that's being simulated through. So the ID of these individuals would mean something if we had covariates attached to them. We don't here, so this doesn't really mean anything. Okay. All right. Does anyone have any questions there?
Rob, no. It's relatively quiet in the afternoon.
Does anyone come back?
We have 170 participants.
170 people who've left their computer on. Okay. All right. So now we have exponential inter-event times underlying our model. So if our data are fully observed, we can generate a likelihood, right, for a given data set. When I say fully observed, I mean that we know when each event takes place. So we know when an infection occurs and at what time. We know the time at which a removal takes place. I will skate over for the moment that is an extremely unrealistic assumption, but we will come back to that later. Right? So for now, we're going to assume that we do know when the event times occur. The likelihood, of course, is just a function which gives us the probability of observing the data, which I'll call D, for values of our parameters. In our case, well, generally I'll refer to the parameters as theta. Generally it's here it's going to be beta and gamma, where this is the SIR transmission rate. nothing to do with the contact network thing. Okay, I can see there are some questions now.
Yes.
Yep.
The first one is how we can covariates. I guess how can we incorporate covariates?
I don't really want to go into the coding now, but so the vignette that I mentioned before is actually on my desk. So she will eventually be in the Journal of Statistical Software, but there's, like I say, there's a preprint up on archive. We go into it all there, but it's basically just, you set it up using the notation that you use for the linear model or GLM command in R. Okay, it's pretty straightforward to do.
Okay, there's two more questions. Both are very specific. First is that, is it that removal rate is simulated from a distribution, gamma distribution in this case? What about the infection rate beta?
No, the infectious periods are simulated from a distribution. So the rate parameter of that distribution is the removal rate, right? If you've got an exponential where it's 1 over, where the mean is 1 over the rate parameter. So we define it in the package in terms of the distribution of the infectious periods, and that parameter is the infectious the recovery rate.
Okay. So there's another question, technical. Just want to clarify the sampling via the algorithm. You simulate the time from the exponential and then the phi1 plus phi2, then decide it's a infection with probability phi1 divided by the sum. Is that about right? Yep,
that's right. Good. And then if a removal, obviously with probability phi2 over the summation, which is just in two events is 1 minus the phi1. Okay. Okay.
So there's one more question. I was going to ask, some paper use other countries' individual level data to estimate reporting delay distribution. When such data is not available or like open access for their region, are we going to touch on this?
No is the short answer to that. I don't quite follow the question. Oh, use other countries.
Yeah, yes.
So obviously, if you're going to do that, you want to try and use data from a country that has similar demographics to the one you're actually modeling in. But no, like I said at the beginning, this really isn't a workshop about COVID-19. It's more of a workshop about models, but these sorts of things do happen all the time, right? That if you want to build a model for things in a country or a city in a country where the data quality is poor, there are shortcuts you have to take, right, or ways around that.
Okay, one more. Yeah, okay, two more now. Can the transmission rate be also simulated from a distribution?
Yep, you can, stick the whole thing in a loop, or use the S-apply type function to generate different values of beta and gamma and then simulate. And of course, in a Bayesian framework, we often would do that, right? When we're thinking about the posterior predictive curve or the prior predictive curve. So yeah, we do that all the time. Okay,
and now we have two more. Can the algorithm be applied to a SEIR model, and will the output of the epi data have the exposure times?
Not yet. So at the moment, the package doesn't cover SEIR models. That's another thing that we intend to change or to extend.
Is there any specific reason that removal rate follows a gamma distribution?
Okay, once again, it's not the rate following a gamma distribution, it's the infectious periods. And it's basically because you might see that in some diseases, right? Often we make an exponential assumption about infectious periods, But that might not be the case, right? It may be that very short infectious periods are less. In fact, it's more likely to be the case, right? The very short infectious periods are going to be less likely than some longer ones.
Okay, one last question. If I receive more, I'm going to hold, let Robert continue to talk and then answer more questions. So this last question is that there are no individual data available. How do we make use of the stochastic model? Would you please comment on it?
In the way I just showed. So that's what I'm doing in that code, right? I have no individual level covariates, and I'm basically telling the model that, the individual level model that. So it is simulating from a homogeneous model. The thing that we will have in a couple of weeks, I hope, is a function that will do it much more efficiently. Okay.
Okay, great. Thank you.
Excellent. All right. So the likelihood, if you write it down, looks like this. We don't need to spend too much time on this, but I mean, you can see that it has an exponential type structure, as you'd expect. The data here, so defined that for this formulation of the likelihood in terms of the series of ordered event times. So T0 is going to be my initial event time, which of course is going to be an infection because you don't get a removal before an infection, which of course T0. And then there's a final infection time, or sorry, event time, TK there, which might mean everybody's been infected and removed, but it might be sort of earlier on in the epidemic, right? We might be talking about data from the first stage of the epidemic with the rest of it missing, right? So this could be the final infection, but it doesn't have to be. And then this T there, the capital T, is basically defining the maximum observation time, if you like. Although let's say the end of the observation period, okay? So I've collected data from the beginning to some point, and this T is that point there, okay? So we can write down the likelihood, oh, sorry, and then of course, I've just got in event times here, but so I need to inform whether we're talking about an infection or a removal. So we introduce this indicator variable delta down here, which is set to 1 if the event is an infection and 0 otherwise. Okay, well, in this case, if it's a removal. So the likelihood is fairly easy to calculate, and we can maximize that, and do all the usual things that we would do with a likelihood. But what I'm going to talk about now.
Sorry, Rob.
Yeah.
Sorry, I was on a bathroom break. Sorry. And there are 2 questions coming in before you move on to the Bayesian. The first one is, by simulating a saturated network, you imply that social connections do not give you any valuable information in your modeling?
Exactly. But I'm only doing this here because I wanted to simulate from that simple model. If I had information about connections in the network, how individuals were connected in real life, that I can now incorporate that in this package, and that's what those models were designed to do. I'm taking a complicated model and forcing it to be simple, just because that's the software available to me.
Okay, and then another question for the EpiDat output, how are event times assigned to specific individuals? Say, when we record the removal time, how do we know it's for, say, individual, coded 294?
Okay, so let's close that. So in this case, well, you can see which individual it is, right? If you had covariates for each of these individuals, vaccination status, how they were connected in a network, we would have vectors or matrices of covariates where each row ties to a certain individual. Okay, so it's defined here. So I could look at individual 273 and see when that they were infected at time 0.25. And then I could go back and look at their covariates and that sort of thing. In this case, these ID numbers are meaningless, because everybody's the same.
Okay, so
okay.
No questions yet.
Okay. All right. So, as I said before, apologies for those of you who are familiar with all this stuff, but I wanted to make sure that people had a basic idea of what we're doing with the inference. So like I say, we've got this likelihood function. We could maximize it. It's very easy to do. We could think, well, we make the assumption that our maximum likelihood estimates are asymptotically normal, and then we can use the sampling distribution to carry out, statistical tests, construct confidence intervals in the usual way. What we tend to do, and although that's very easy to do for the analysis I'm talking about now, it's going to be more difficult later on. Right? And so what we tend to do instead is think about doing the inference in a Bayesian framework, and we combine the likelihood function with a prior distribution or density for our parameters and carry out Bayesian inference. Okay, so we have a posterior distribution. It's given by Bayes' theorem. Okay, so it's the probability of associate or probability density for the parameters given the data. Okay, which is equal to the likelihood times that prior divided by this normalization constant, which we get by integrating out the parameters from the numerator. Okay, so once we've got that, we end up with something that's just, it's a scalar that depends on the data. Okay. Okay, so hopefully that's all familiar with you, familiar to all of you. So the priors, just a quick word about that, are a distributional representation of our belief about the parameters before we've seen our data. Okay, so if you've never done any Bayesian inference, this seems a weird thing to think about, your belief about the parameters before we've seen the data. But it's actually, I mean, you could argue it's how we sort of live our life, right? We have belief about things which hopefully we update when we get new information, okay? So hopefully that makes that a little bit easier to deal with conceptually. So we choose whichever distribution best represents our belief, generally, right? Sometimes we choose them for mathematical reasons, but if we've got a parameter that's somewhere on the real line, we may well choose a normal distribution. If it's positive, we may choose a gamma or exponential, etc. And then we parameterize that to express or to characterize our belief. Okay, so it could be strong belief, or it could be quite a weak belief. The prior can come from various places. So it could be representing expert knowledge. So I could talk to epidemiologists who actually know something about COVID-19 or whatever disease I'm data from I'm analyzing. I could talk to them to get their belief about the disease system and use that to come up with my priors. A nice thing about the Bayesian approach is that the prior can be your posterior from the analysis of different data. So it gives us a way of combining different data sources, and it's very nice in a sequential situation, right? So if I've got new data coming in every day, I can use my posterior distribution from yesterday as my prior belief for today and incorporate the new data coming in, which is computationally more efficient than analyzing the whole data set every day. All right. In lots of situations, we don't want to make strong prior assumptions or incorporate strong prior belief about the parameters, and there are various things we can do. We can think about things like Jeffreys priors or reference priors, which essentially give us flat priors that are invariant to transformation, quite often we can get away with cheating and just, we take our normal prior and we give it a large variance. So it's flat in relation to the likelihood. And we can and should generally do our analysis with more than one type of prior to check the sensitivity of the results to those priors. So conceptually, the essence of the Bayesian approach to parameter estimation, okay, so I'm ignoring things like goodness of fit, model comparison, I'm just thinking about the estimation for now, is that the posterior is proportional to the likelihood times the prior, right? The normalization constant's just there to ensure our posterior is a density. But this is where the action is for estimation. So conceptually, we're starting with a prior for our parameters, express our belief about the parameters before we've observed our data. We then update that belief with the information in the data via the likelihood to get to the posterior. Okay, everyone's still with me? That's a very silly question to ask a Zoom audience.
Yes, and so far no questions.
Okay, so before I can go back to the model, I do also need to talk a little bit about the computation behind doing this, okay? Because as I'm sure most of you are aware, the posterior distribution, which is, a very useful object, it summarizes all the information or all my belief from both my data and my prior belief about the parameters. It's a useful object. The trouble is we generally can't write them down, okay? And we can't write them down, well, we don't have a closed form solution for them because that normalization constant contains an integral that has no closed form solution, okay? Not always the case, right? If your likelihood is representing a fairly simple model and you choose the right prior, sometimes this can work out. And we will see an example of that actually in a few slides' time, but generally we can't calculate that thing, okay? So what we do instead is we turn to Monte Carlo inference, okay? So this is inference, inference via stochastic simulation. Okay, so the basic idea is that we find a way to sample from the posterior distribution. Okay, so we're generating random observations, which are actually just instances of the parameters. Okay, theta, of course, is likely multi-dimensional. We can generate those from the posterior distribution. We can use that sample to estimate things about the posterior, right? We can plot the posterior itself, right? Take a histogram or a smoothed density plot of the parameter realizations. We can find the sample mean to estimate the true posterior mean. We can find the sample median to estimate the true posterior median, etc., etc. Okay. How do we sample from the posterior? So there are actually a suite of different ways of doing this, but one of the most popular ways and the way the method that our software package uses is Markov chain Monte Carlo, so MCMC. The basic idea here, we're talking about discrete time Markov chains. I should make clear to start with. So the basic idea, of course, with the Markov chain is that the state at the next point in the chain is generated from some probability distribution that only depends on the previous state, right? So stochastically, I can simulate my next state by just looking at time t. I don't have to worry about time t minus 1, t minus 2, etc. Okay. So we have a form of conditional independence. Now, Markov chains, if you set them up in the right way, have a stationary distribution, okay, which means that wherever you started off in the state space, and the state space, of course, is the parameter space. So when I talk about the state of the chain, I'm talking about the current parameter values that we have. So yeah, wherever you start the chain off in the state space, it ends up in the same place. Okay, so there's a toy example here. I've set this is an example of what's called a random walk. Started them off from different points, and they both end up basically around here. And if I took this and, you know, looked at a histogram of that, that would represent the stationary distribution of this Markov chain. Okay, the basic idea is stochastically, if I took a chunk of observations there and a chunk of observations there, statistically, I shouldn't be able to determine a difference between those two samples if we've really reached stationarity. Okay. All right. So what MCMC does is it sets up a Markov chain. So we update our parameters at each point in the chain, which has a stationary distribution, which is the posterior distribution. Okay, so once we've run our MCMC chain, we discard the first bit, which we call the burn-in, because obviously these haven't reached stationarity there. And then the rest of this we can treat as dependent samples from the posterior. Okay. Often we will, rather than looking at all of these samples, we might take every 10th or every 20th, so that we cut down on some of the dependence there. But often that doesn't really matter. Okay, but that's the basic idea. All right. So that might sound difficult, right? Set up a Markov chain which is going to converge to the posterior distribution. It actually isn't very difficult to do, and there are a number of ways to do it. Probably the most popular and most general method is something called the Metropolis-Hastings algorithm, which has a number of special cases. There are other methods as well. There's Gibbs sampling and Hamilton Monte Carlo, both of which often work more efficiently than Metropolis-Hastings. But Metropolis-Hastings is very general and can be used in a lot of scenarios. The special case that we're going to look at is called random walk Metropolis-Hastings, or just the Metropolis algorithm. Okay, so it was actually a forerunner for the Metropolis-Hastings algorithm, which is a generalization of the Metropolis algorithm. And for those of you who can't wait to get past this bit, we're nearly there. I'll just describe briefly how this algorithm works. So the basic idea is that we start off with some arbitrary starting point for our chain. Okay, so I drew my Markov chains here were in one dimension. Remember, if I've got 3, 4, 5 parameters in my model, the parameter vector is actually multi-dimensional. But I would set each of those parameters to some value, shouldn't matter which, and then I'm going to use the following algorithm to generate my chain. Okay, so I generate an observation Z from a distribution F, where F is symmetric around 0. So typically we would choose a normal distribution with mean 0, but you can use a T or a uniform or come up with something more bizarre, if you like, or a Laplace, whatever it is. We generated that noise, symmetric around 0. And then what we do is we generate a candidate value for where we might move next in the chain. We're not definitely going to move there, but we might move there. So I call that theta prime. And theta prime is just where I am currently in the chain. Okay, so the current parameter values plus that noise. Okay, so in one dimension, I'm going up a bit, or I'm going down a bit, and whether I go up or down has equal probability. Right? If I've chosen a normal, then I'm more likely to move a small distance than a large distance, or propose, I should say, a large distance away from where I currently am. I then calculate an acceptance probability that I've called alpha. Okay, this is actually going to change each MCMC iteration or each Markov chain iteration. But that is the minimum of 1. And the posterior under the proposed parameter values divided by the posterior under the current parameter values. Okay, so where I am currently in the denominator, the posterior about where I might go in this parameter space in the numerator. Now, some of you, I've given it away. Obviously, I said earlier that we can't calculate the posterior because we can't do the integration required to get the normalization constant, but we don't need to, right? The Z there is a function only of the data, not of the parameters, because we're integrating the parameters out. So they, the normalization constants cancel out, and what we're left with is just a requirement to calculate the likelihood under the current, the current and the proposed parameters, and the prior under the current and the proposed parameters. And I can calculate both of those. We've written down the likelihood for this model, and the prior is what I chose, right? So it's going to be some density that encapsulates my prior belief. And then the final step is that we accept that proposed value of the parameters as our next point in the Markov chain. So I set that equal to theta I plus 1. I do that with probability alpha. Otherwise, I stay where I am, I reject that theta prime, and I set my next point in the chain to where I am currently. Okay, and that's obviously with probability 1 minus alpha. And then I repeat that over and over again. Okay, and what that will do, once again, I'm back in one dimension. Generally, we're doing this in multiple dimensions, but if my posterior or my likelihood times my prior look like this, you'll see that what happens is if I'm at a particular point and I propose to move to a higher, an area of higher posterior mass, this ratio ends up being greater than 1. And so alpha equals 1, because it's the minimum of 1 and something larger than 1. So I will accept that move, right? So if I propose to move up the hill, I always accept. If I'd proposed to go the other way around, so I'm moving down the hill, then I work out this ratio, which will give me a probability of accepting that move, which basically depends on how far I'm going down. Right? If I'm going from the top down to the tails, I will have a very low probability of accepting that move. If I'm going from the top to somewhere a little bit lower, I have a higher probability of accepting that move. And so when I propose to move up, I always accept. When I propose to move down, I accept probabilistically based on how far I'm proposing to move down. And that will give me a chain, you can sort of see, and it's quite easy to prove, that will follow this distribution. Okay, so once I've done that, I can take that output and use it to estimate things about my posterior distribution. The last thing I'll say on this, of course, is that in the multi-parameter situation, which is what we're usually in, we can update these parameters one at a time or in small blocks, which actually makes the algorithm much more efficient than trying to update all of the parameters at once. Okay, but I won't go into that. But this gives you a general flavor of what we're trying to do. And I'm guessing from the movement at the top of the screen, there was a question.
Yes. The method seems to assume a unimodal posterior distribution. What about when you have something bimodal or even more complicated?
Okay, so it doesn't assume a unimodal posterior distribution. The algorithm will work of any sort of shaped posterior distribution. And of course, in most complex models, we will have a multimodal posterior distribution, or at least, well, that happens quite a lot. And you also get sort of ridges where there's high correlation between parameters and things like that. So thank you for that question, because you have reminded me to think about something I was going to skip over, which is that this algorithm will work for any distribution F I choose, as long as it's got common support, right, the support required. However, it will work, it's guaranteed to work with infinite time, right? And often we don't have infinite time to spare. So actually, the practical difficulty of algorithms like this is choosing this distribution, and specifically its variance, so that it does move around the posterior distribution efficiently. Okay, so let me tidy this up a bit. So if I have a posterior like that, and I choose an F with a very large variance, then what will happen is, if, say, I'm at this point in the parameter space or parameter line, I will generally propose to move very far away from where the posterior mass is. Okay, and then I will end up rejecting most of those moves, and I end up with a chain that does this sort of thing. You know, it moves every now and again, but we have lots and lots of rejection points. Okay. If, on the other hand, I set it to be too small, the proposal variance, so I'm talking about the proposal variance of F, then what happens is I always propose to move very close by. Okay, this ratio ends up being close to 1, and then I always accept my moves, or almost always, and we move around really slowly. Okay, so you have to be very careful about choosing that proposal variance. There are adaptive methods that people commonly use nowadays. Unfortunately, some of the models, in fact, the last model we're going to talk about later on, the adaptive, we've never managed to get the adaptive methods to work for that model. So some of this stuff you do have to sort of do by hand for some of the models that well, not by hand, but you need to tune them, right, to decide what that proposal variance is. I'll just say quickly, so going back to your question, if you've got a multimodal posterior, then that does make things more difficult, right? So the proposal variance, which allows me to move between these modes, might be different to the proposal variance that allows me to get between them, right? So you can get stuck in these modes, and then you end up with chains that do that sort of thing, which is also problematic because you'd have to run that for a very long time to reach stationarity. Okay, so there are more complicated things that you can do. You can use proposal distributions, which are mixtures, for example. So sometimes they jump a long way, sometimes they jump sort of close by.
Okay, thank you, Rob. There's no more question.
Okay, that was a long answer, wasn't it? All right. So there's the basic idea to the way this package is doing the inference. So I'll go back to now the stochastic SIR model. And there's the likelihood equation again that we had before. Like I say, there's no reason why I can't just maximize this and do maximum likelihood estimation for this problem, okay? But we're not going to do that. So I now have data which looks like this. Remember, I've got my event times, k of them ordered, and then I have these indicator variables that define whether that event was an infection or whether it was a removal. And I've got a parameter vector that has two parameters in it, the beta and the gamma. So if we know those event times, we know when the infection times and the removal times occurred, we just put prior on our two parameters. Usually we assume a priori independence between the parameters, but we don't have to do that. But we put our prior on the parameters and then use the estimate of the MCMC to generate samples from the joint posterior distribution given there. Okay, now I'm not going to do that here. I'm actually going to use the EPI-LMCT package to do something even simpler. I could argue, you know, it's nice to do simple things, but actually the real reason I'm not doing that is because the software right at this moment won't let me run that analysis. It'll let me run a simpler one and it will let me run the more complicated one. and we'll come on to the more complicated one later, but it won't let me actually run that analysis, or at least not as far as I can work out. But like I say, this should change over the next couple of weeks. Anyway, so what I am going to do is, I haven't actually given the likelihood here, but you can rewrite this likelihood function. You can see that it's all made up of multiplicative parts, right? So you can actually separate out a component which is a function of beta. Okay, so L1, what I'll call the likelihood for beta, and the likelihood for gamma. Okay, a function that's just in terms of gamma. Okay, and you can see that I think the first people to show this was Phil O'Neill and Niels Becker in 2001. But we actually talk about this as well in one of our papers in the supplementary material, which is what I used to prepare this. But then both the later paper has links to the earlier paper. So what I'm going to do using EPI-LM is to separate those two analyses in two. I'll look at the transmission rate first, and then I'm going to look at the infectious period. Okay. So I'll start off by just concentrating on trying to estimate the transmission rate. So in a Bayesian framework, I've got the posterior of beta, the transmission rate, which is proportional to its likelihood times the prior. And yeah, I don't really need this bit, but so this is what the analysis that I'm going to carry out based on this.
So Rob, there is a question on the likelihood.
Oh yeah.
Yeah, could you please explain about the form of the likelihood, why there are no delta i's inside the exponential part of the likelihood function if they indicate the event type of the i's observation?
Are you? Oh, you mean in the likelihood over here? The way it was written down here.
Mm-hmm.
Can I explain that off the top of my head?
So, yeah, the delta I is inside the exponential part of the likelihood function.
Yeah. Off the top of my head, no, I can't. I'll tell you what. If you send me an email afterwards, I'll give this some thought. I'd have to sit down and look at the math. But yeah, no, off the top of my head, I don't know.
Okay.
Well,
John, please. Yeah.
Anyway, but it works out that way. I'm pretty sure that's right.
Okay.
It's in two papers, so I really hope it's right. Okay, so I'll go back to that and I can let you know via email. And did you say there was another question?
That was it. Yeah. Zhang Zhang, you asked a question, so please contact Dr. Deardon, follow up.
Okay. All right. So I'll go back to, yeah, let's ignore that. I'll go back to this was the data that I simulated previously, okay, using the EPI-LM package, showing the infection times and the removal times. And now I'm going to fit that model to that data. Okay, so here is the code to do that. There are various things going on here, but note that actually a lot of this is comments. So what shall we start with? Well, we'll start at the beginning, shall we? So what's going on here is this line, the SustCov and SustCov up here is a vector. The first entry in that is a list containing information about beta, the transmission parameter. Okay, so I've put a gamma 1 prior on that beta. The true value you'll remember is 1. You don't have to have well, that's actually a fairly non-informative prior for that parameter, but you can make it less informative if you want, and that will still work. This was really an arbitrary choice. And then the 0.001 here is my proposal variance. Okay, so I I will change that in a minute, but I played around until I got something working out reasonably well for beta. Okay, this is a proposal variance for a normal proposal, so I'm adding Gaussian noise in my MCMC chain. And then this is the starting value. Remember, we had an arbitrary starting value for beta, so this is where I'm starting my chain at 0.03. The next line here is basically just telling the EPILM-CT function that I have no covariance. Right, so I have 500 individuals, and I could tell it what my covariate values are there, but actually I set that equal to 1, which just tells it there's no covariate information. Okay, no covariate information related to your probability of getting the disease or your rate of getting the disease, what we call susceptibility covariates. Okay, then just to start this off, so like I say, I could run this using, say, an adaptive MCMC function, which is commonly how we would do these things, because the EPILM package does allow us to just produce the likelihood. But here I'll use our MCMC engine just because it will be consistent with what I do later on. So my command, oh, sorry, yeah.
There is a question. So you're essentially doing a two-step thing where you sample random event times, then the rest of the analysis is conditional on this as data, right? Is it possible to model it all jointly, or is it too complicated in practice?
No, so we're not really sampling random event times, right? I mean, earlier on, I simulated the event times. What I am doing now is the event times I'm assuming I know, right? So I have split the analysis now into an analysis which estimates beta and an analysis that estimates gamma. Okay, but it should end up in the same place because, as you saw, the likelihood has those two marginal components. Okay, like I say, we are introducing to this software package the SIR function. So one, things will be more efficient, but also it will by then, we will be able to fit this model jointly. Okay, did that make sense? Once again, I just have to assume that silence means that it makes sense. All right, so the command for running the MCMC is this. So I'm defining the data. I'm telling it it's a known epidemic, which basically means I know the event times, I know the removal times and the infection times. I'm just going to run my MCMC to start with for 2,000 iterations to see what happens. And then this is just setting my individual covariates and the information for the prior, etc., which I had up there. Okay, and this will plot my output. So if I look at the output, you can see that what happens is the MCMC chain very quickly jumps down towards where the posterior mass is. And, you know, it's doing a pretty good job in 2,000 iterations. That looks fairly good, but of course I can run it. This took, you know, seconds. So I can run it even though the underlying likelihood calculation is very inefficient. This was just seconds. So I can run this for longer. If I run it for 20,000 iterations, and I've actually changed the starting value to make it nearer to the posterior mass. And I've also changed the proposal variance to try and make it a little bit more efficient. I'm not sure if that worked, but this is what I get out at the end. Okay, so that's the sort of thing that we're looking for. You might argue that if you look at the thick bit here, we can see some autocorrelation. So maybe I'd want to run this for longer, but this is giving me a good idea of what's going on. The other thing that I will say is that typically what we do in MCMC is not just run one chain, we'll run lots of chains, preferably from different starting points, because that enables us to, one, check the convergence, but also if we're running those chains in parallel, it's much more computationally efficient, right? Because we can get more observations from our combined chains at the end once we throw away the burn-in period. And we can do that in EPI-ILM CT. It makes all the notation and code look horrendous. So I didn't do it here. I just did it for one chain. Plus I was in a rush. I was trying to put a workshop together. Okay. So if I take that output and do a density plot of that, we can see what the posterior for the beta parameter looks like. Okay, so the true value was, I think, 0.01, and you can see we're getting a mean or a median around, well, close to that. I don't like this bumpiness at the top, so I'm not quite sure whether I need to change the bandwidth on the density smoothing to just make that look smoother, or whether it's problem with the convergence and maybe the MCMC has not really converged, so I should run that for longer, run multiple chains to make sure of that. But like I say, I was doing it in a rush. So for now, we'll just assume that that's smooth. From the Bayesian point of view, we don't think about confidence intervals in terms of, you know, what happens over repeated realizations from the sampling distribution. We have a probability distribution which captures our belief and our uncertainty about the parameter. So I can simply, or the simplest thing I can do is I can cut off 2.5% here and cut off 2.5% here and use these points here to provide what we call a credible interval, which is, you know, essentially a Bayesian confidence interval, but it's a probability interval in the sort of exact sense. Okay, but that enables me to capture my uncertainty, and I've done that on the next slide. You can see I've got a summary command up here. A couple of things going on in here. So this start parameter is defining the burn-in. So I'm doing this summary only for the last 19,000 iterations of my 20,000, which is actually the same that I did over here for my plot there. I cut out the first 1,000 of those. So that's the burn-in. And also I've thinned this, so I'm only looking at every 10th observation to try and cut down the autocorrelation. Okay. What I didn't do and what I should do is actually check the autocorrelation function and blah, blah, blah. Okay. So you can see my posterior mean there. There's the posterior standard deviation. And I've got the quantiles here. So my 95% credible interval or percentile interval is given by this here. Okay, so that expresses my, I have a 95% belief that my parameter lies in this interval. And remember, the true value was 0.01. Okay. Does anyone have any questions there? I'm going to go on to talk about the removal rate now and how we can handle that.
Rob, there are no questions right now.
Okay. So the removal rate side of things, okay, so I've got this other function. Well, remember that my infectious periods were basically just generated from an exponential distribution. So that likelihood, that L2, or that component of the fall likelihood, is just a product of exponential densities, or, well, more generally, it might be gamma densities, right, if I decided to do it that way. Where I have a bunch of observations which are the actual infectious periods. Okay. Now this is only possible here because I know the infectious period for each individual. So I can simply analyze those infectious periods to estimate the removal rate. Okay, I'm basically assuming my infectious periods come from an exponential distribution. I can write down the likelihood for that. That's, you know, just a product of exponential densities for each of the infectious periods. If I want to do this in a Bayesian framework, I can do a conjugate analysis. So I can put a gamma prior on my infectious period rate, or the recovery rate, right? The gamma there. So if I put a gamma prior on that with parameters A and B, so I choose A and B to express my prior belief about that parameter, you can show mathematically that the posterior for my transmissibility parameter is also a gamma distribution. It's a conjugate analysis, and this is what that gamma distribution is, right? So everything here is analytically tractable. I don't need to use the MCMC. So I can work out the mean of that gamma. I can work out the quantiles, the median, whatever it is I need. And note that what we have in here, so that the first parameter there depends on the prior, and the sample size, which I think previously we called capital N, right? The sample size then, and the second parameter is given by B plus the rates of, but plus the sum of all the infectious periods. Okay, so everything's analytically tractable, and my posterior for the gamma looks like this. It has a posterior mean of 0.93. The true was actually 1, you'll remember. If I want to work out the posterior mean infectious period, I'll just take 1 over 0.93, and that's 1.07. And I can work out my credible interval, which turns out to be for gamma 0.70 at the lower end, 1.23 at the upper end. And I can invert that if I want a credible interval for the infectious periods. Okay, so just to reiterate, I've separated these two, the two parameters into separate analyses because of limitations I currently have with the software. Okay, there's no reason why we can't code up that likelihood and run the whole thing as a joint estimation. And hopefully you'll be able to do that in a couple of weeks when that new functionality is in the package. Okay, I think I have some questions.
Yes. So the first one is about the standard error. What is the difference between the naive SE and the time series SE?
That's a good question. So I'm guessing, but I've never actually thought about it, but the time series SE must be taking into account the autocorrelation in the MCMC. If Waleed's online, he can explain. But I'm assuming that's what happened.
Okay. So the next question is that, is there only the single beta and the single gamma? And if so, is it feasible to bypass MCMC and compute the normalizing constants using the quadrature?
Yeah, I mean, yes, you could. And we are, and in this situation, we've got two parameters, even if we estimate them jointly, right? So we could use rejection sampling, quadrature, and it will all work fine. We don't really need MCMC to crack this nut. The reason I'm using it is, well, one, it's what we've got in the software, but the analysis I'm going to show you in a few minutes, we do need the MCMC, or we certainly need something that can handle higher dimensions than something like quadrature can.
Okay, thank you. Next question, why doesn't the simplification for the gamma posterior work for beta as well? Looking at the likelihood, the ST factors seem to be the only difference in the beta terms. If all event times are known exactly, isn't the beta term a similar product of exponential terms?
Honestly, I didn't look at it, so that may be the case. I was trying to show in the workshop how the software works. So that's why I've done it this way. And also because it's going to lead into the more, this is not a realistic analysis, right? Knowing the infection times and the removal times. So I'm trying to set it up for the more complicated analysis later on. But yeah, that may be true. In fact, yeah, it probably is true, but I haven't actually looked at it.
Okay, thank you.
Was that the same Sean that I used to teach at Guelph? He can maybe let me know. I always remember him. No? Okay. That Sean used to ask annoying questions as well. I'm only joking. They're not really annoying questions. Okay.
Last one for the moment. What is the advantage of not using conjugate prior and using MCMC?
The advantage, well, I wouldn't really put it in those terms generally. I mean, often the conjugate analysis doesn't exist. So in the analysis we'll look at in a few minutes, there isn't a conjugate prior I can put on things for the closed form solution to work. So in lots of situations, the conjugate analysis is not possible. So it's not really a question of advantage, it's whether you can do it or not. I suppose there is a conceptual issue, right?
Yeah, there is a concept, yeah.
With a conjugate prior, in that the prior is supposed to express your belief, but if you're using a conjugate prior, you're really picking a prior that enables the math to work out. So there is a conceptual issue there.
Okay, so no more questions for now. Thank you.
Okay. All right. So with that in mind, we're going to complicate things, and we're going to complicate things to hopefully make them a bit more realistic. All right, so there again was, well, that's the first, sorry, I've still got my question and answer open here. There again, you can see the likelihood written in that original form. But that analysis assumed, like I said, that we know the event times. Okay, we know when infection occurs, we know when removals occur. That hardly ever happens. Okay, the best you ever, that's not necessarily true. I mean, one situation when you're, say, in an experimental setup and you're looking at the infection of a plant or animals, is that you might be able to collect that data recording at discrete time intervals, right? So I might know, I go out on a particular day, I test all my animals, or I look at my plants to see if they've got some rust spores on them. And then that will tell me that the infection occurred within a given interval, right? That hardly ever happens in human situations. What happens in human situations, best case usually, is that the disease is reported some time after infection. Okay, so we have a form of left censoring. I get a disease. If it's a serious disease, I go to the doctor, there may be a lab test. I know the infection occurred before that. In some diseases where there's not so much variability between people, we may have a very good idea about when the infection occurs, but often we don't, right? In lots of diseases, and especially COVID-19, the actual expression of that disease is quite different between different individuals, and things like infectious periods are probably quite different between individuals as well. So we don't see those. Similarly, or maybe even worse, the removal times are almost never observed. Okay, so normally I don't know when an individual stops shedding enough virus to be infecting other individuals. Okay, the exceptions to that might be if we assume that lockdown is really stopping infection. Well, it isn't really, right? It's infections probably still going on within the house, and some people are breaking lockdown stipulations or self-quarantine stipulations, or in situations with animals or plants where the control method may be culling. So in foot and mouth, if you had animals with foot and mouth disease on your farm, or even if you were thought to be at high risk, the government veterinarians would come on and they would cull all the animals. So then you could assume you know the removal time, at least to some degree. So sometimes we can do something to infer these things in a sort of rough way based on symptoms, based on how the disease works, but often we can't at all. And COVID is an example where I think it's difficult to do that. So what we had before in our simple situation was this SIR model. I assume I know the infection time. I assume I know the removal time, which means I know the infectious period. Okay, and that's why I could split the analysis in two, because I know all of these infectious periods here. More typically, we have this sort of situation where I don't observe these, the removal time and the infection time. What I observe is maybe a notification time. And that notification time could be a lab test, it could be when symptoms are developed. It's going to depend on the scenario as to what that actually means. I've also assumed here that it occurs between I and R. It may not, it could occur before. Well, I can't, no. In an SEIR model, sorry. So if that was an SEIR model, it could occur before infectiousness occurs. And it could occur, I don't know if disease is where this is the case, but it could occur after removal, right? You could have a situation where you display symptoms after you've stopped being infectious. But I think this is more typical, that you would see the notification would occur within that interval. So we then reformulate this problem. We think there are two things now that I don't know. Well, more than two, but they're sort of functions of each other. I'm going to reformulate this in terms of an incubation period, which is the period between infection and notification. Technically, we usually use incubation to mean between infection and symptoms, but I'm going to use it more generally here to be whatever that notification time is, lab confirmation or whatever. There's an incubation period for each individual who gets infected that I don't know, and there's a delay period, so the time between notification until removal occurs. And so what we would do is we'll say we'll have a whole bunch of incubation periods, latent variables, sort of like random effects, right? Things that I want to estimate, but I'm not really interested in. And I'll assume that they follow some distribution. Okay, usually we assume they follow an exponential distribution, but it could be a gamma. Okay, so but now I'm going to try and estimate all of these things, as well as the parameters of the distribution that the two periods follow. Okay, so I've now moved to a situation where my data looks like this. Okay, so I've got it D minus because it's sort of a less informative data set than what I had before. But basically I have a set of notification times that I'll call Z, right? So Z1 up to Z, the number of cases, preferably the number of infections, but let's just call it the number of cases for now. I then have a series of incubation periods that I'll call rho inc for each of those cases. And I'll assume they follow an exponential distribution with parameter gamma inc. And then I've got all those delay periods, and I'll assume that they follow an exponential distribution with parameter gamma del, okay, or gamma delay. So I now have a whole bunch of these nuisance parameters, all these rows, 2 for each individual that got infected. Now, if I have managed to estimate or infer in some way those in delay and notification periods, then that defines my infectious period. Right? The way I set this up, my infectious period is the summation of those two things. It also defines my infection times. Okay, so the notification time minus the incubation period gives me the infection time. So that should really be, delta equal 1. And the removal times as well. Okay, so the notification time plus the delay period tells me when the removal is happening. So T delta equal 2. Okay, so now if I've inferred those incubation and delay periods for each individual, I can calculate my likelihood. Okay. And what we do is we reframe the problem, which is very typical in Bayesian inference. We use something called data augmentation. So I've got this data set now, which is the notification times. And then my parameter set has been augmented. It's got my original transmissibility parameter. My removal parameters have been divided into 2 parameters. So I've now got 3 model parameters. And then all of these latent nuisance parameters that I need to infer. Okay, this is called data augmentation. And what I would do is use my MCMC algorithm to sample from the joint posterior of the model parameters, these 3 things, and all of those latent parameters as well. Okay. Typically, I would do this, like I said before, you would update these parameters individually in your MCMC algorithm or in small blocks rather than one big multivariate block. And that's why MCMC is a good way to tackle this problem, because it does enable us to update the parameters one at a time or in small blocks, which is more efficient than trying to handle a 1,000-dimensional parameter vector in all in one go. Okay, I need a swig of coffee. So are there any questions at that point?
At this point, no. Thank you.
Okay, I have to be a short swig of coffee then. All right, so I've got my 3 model parameters. They each need a prior. One thing, the rows, sorry, these nuisance parameters don't need a prior. In fact, in a sense, they already have a prior, right? Back here, I assumed, well, then this is not really a prior, it's part of the model, but I'm assuming that they follow a distribution. We call this an observation model, but you can think of them as a prior for those latent parameters. But this model now is overspecified and unstable. Right? In fact, I think I'd go as far as to say it's non-identifiable, or at least very poorly identifiable. So when we do our Bayesian analysis, we do want to use informative priors. So another reason, as well as the computational machinery that we get through MCMC, another reason that we like to do this in a Bayesian framework most of the time is that we do need to put informative priors on those parameters. Okay, if you think about the likelihood, what the likelihood looks like for this sort of problem here, I could get a very high likelihood if I choose all these incubation and delay periods in such a way that everybody gets infected at time 0. Okay, so if I set those to the right values, everyone gets set at time 0. And then if I give a large beta, it doesn't really matter what these, well, these would have to be set so that they enable these to go near 0. But you can see that you'd end up with a spike of likelihood at time 0, right? So there's an overspecification problem that we have here. And so we want to put informative priors on, well, preferably all 3 of our model parameters, but whatever information we've got, right? And what that does is it puts more posterior mass in a reasonable part of the parameter space, and our MCMC explores that, rather than going off to areas of high likelihood and thus high posterior mass, which are actually not realistic, right? And this is a very common thing in Bayesian analysis, where you can use overspecified models and then use your prior to tie them down to something reasonable. Okay. The downside, of course, is that with the data augmentation, and you can argue I've got a much more realistic view of my data now, I've got a much higher dimensional problem. Okay, I now have a joint posterior of the model parameters, the incubation periods, the delay periods, and their parameters. So, you know, I've now got what? Previously I had 2, now I've got 3 parameters plus 2 times the number of cases. Okay, so if I've got 100 cases, I'm up to 203 parameters. If I've got 1,000,000 cases, you know, I'm in the realm of computational intractability until we get our quantum computers. And of course, in the MCMC, the likelihood function needs to be calculated, or the posterior up to proportionality needs to be calculated many, many times for different values of those parameters. It's even worse if we really have an individual level model, because then all of those all of the transmission rates differ between individuals. So the likelihood is even worse, right? So it can quickly become a computational morass. But I'm going to show you how to do this in EPI-LM-CT. Actually, are there any questions before I?
Yes, there are 2. The first one is on data augmentation. So why is it called data augmentation if you're adding a bunch of unknown parameters?
Good point. So often, and you can think of this in this setting, those parameters represent data, right? So if I had missing covariates in a linear regression, I could treat those covariates that are missing as latent parameters. So I'm augmenting my parameter set with the data. That's less clear here, but in a way it is data. I mean, the data I would like to get is the infection time and the removal time. And by sticking in those latent parameters, I can get those, at least conceptually. So yeah, I've never particularly liked the word, the phrase data augmentation, but that's what it was named.
Okay. So next question, and first, thank you very much for clearly explaining the setup for estimating the infection times and the removal times. Can we extend this to a SEIR model to estimate the exposure times by modeling the latency period?
We can completely. So yes. Okay. So we would have a latent period. Hold on, that's not right. Drawn that in the wrong place, haven't I? That's S, that's E. We would have a latent period, an infectious period, and then a removal period. And of course, you'd have to think about where your notification is going to occur, right? But now we would want to estimate this period, and that period, or you can set it up in whatever way you like, right? But you'd have an extra period that needs to be estimated if you did an SIR framework. And that's what people commonly do.
Okay.
Okay.
Yeah, okay, so I see a question. I was just happen to check the chat. The question should be sent to Q&A, but here you go. If you infect everyone at the time, okay, if you infect everyone at the time 0, do you get a sub-exponential process?
Yeah, I shouldn't say at time 0. I should say at something close to 0, right? So very, very close to 0. So yeah, if it was actually 0, it would be sub-exponential. Yeah, but the point is that you can get areas of high posterior mass which are obviously not plausible and don't match the data because the model is overspecified. Yeah, similar problem in mixture models, right?
Thank you. Yeah. So just remind everybody, if you have a question, please use the Q&A, not the chat. Thank you.
Okay.
Yeah.
All right. So a lot of this you've seen already in the first example. Well, I'm setting up my library again. I'm generating my contact network with a probability of an edge between each individual. But you'll notice here that I've cut it down from 500 to 100 individuals. And that's because this analysis is much more computationally intensive. Okay. The type of model I have here is an SINR. Okay, the kernel type is network. Don't think anything else has really changed, except now we need to put a prior on, well, actually what we do here is we put a prior on the on the incubation and delay periods. It's not actually on the rate. So you need to invert that to think of what the prior is on the rate. And that's defined up here. So the prior I'm putting on the incubation and delay periods here are gamma 1.25 in both cases. So I've got a mean incubation period of 4 and a mean delay period of 4. And oh yeah, in this case, the true transmission rate parameter, is that right? Okay, I'll come back to that in a minute. I think that might be a mistake, but I'll come back in a second. Okay, but I basically put this the priors on the incubation periods and delay periods. They are informative, right? And they're informative because of that stability problem. So if you were really doing this analysis for publication or for use in public health or animal health, whatever it is, you'd really want to do a sensitivity analysis on those priors, and you'd with those priors, and you'd really want to think about the evidence that you use to come up with those priors. Okay, but if I run this, I'm showing. Oh no, sorry, I'm getting ahead of myself. This is not the MCMC analysis. What I'm doing here is actually generating the data. Okay, so I'm generating a new data set with 100 individuals. The transmission rate, the beta, is 0.005, and these are not priors at all. These are the incubation periods and delay periods. Okay, so please forget what I just said. We'll come on to that in a minute. So if I simulate all of that, I get an epidemic that looks like this. So I've now got 3 curves. Once again, I'm going to ignore this one. So I've got the infection times. You can see that the infection times, which I'm assuming I don't observe, right? They have a mean of around 13, 14, or a peak, I should say, of around 13, 14. The notification times are occurring somewhat after that, roughly 4 time periods after. And then my removal time, well, actually this should have shifted about 4 on average, but in this instance, it's only been shifted a little bit. Or it might be about 4, almost 4. But the other thing that you can see is that a number of these removal times have gone off to sort of quite a bit longer in the epidemic. Right, so most of all the infection is actually over. The infection times are over by time 25. We're getting notification times, which are sort of over by about time 27, 28. But the removal times are much further than that. Right, so we have substantial amount of variation going on here. All right. So the MCMC analysis, I think I'm going to skip over the code here because I'm a little bit behind in the time, and I think this is no, this bit is not self-explanatory. Okay, so one thing I will mention is the way we've set this up is that I have what's called a Sparks term. Okay, so my incidence rate here is, rather than being beta times S times I, which is the model I'm trying to fit, right, or the incidence rate for the model I'm trying to fit, I am allowing for infections that occur at random, okay, to particular individuals through this term, the Sparks term. Now, the reason I can switch this off, but actually I keep it in because it helps with the MCMC mixing, right? As the MCMC chain's moving about and the delay periods and removal periods are changing, you can get stuck in areas with low, with zero likelihood in the individual level model case. Okay, I don't think, oh no, it can still be a problem here, right? We can end up with situations where someone gets infected who can't possibly have been infected. So this Sparks term is basically there to help us move around the parameter space. But I don't really want it in the model. So I put a prior on it, which forces it to be low. Okay, so this is my my gamma prior with mean 1 over 100,000. In reality, this Sparks term would represent infections coming in from outside the population, things like that, but it also, in the individual level case, will capture poor model fit. Okay, so it's unfortunate that that complicates this slightly, but just bear that in mind, that we have this extra parameter that we don't really want. The rest of it, I think, is similar. So I'm setting up my prior for my transmissibility rate and no covariates for my individuals. This should be 100. I've had a cut and paste error, that looks like. This is the information here on, or sorry, it's actually down here as well, on the priors for the priors and the initial values of the incubation and delay periods, or their parameters. Actually, the priors are here, right? So the priors I've put on are informative, okay, because they need to be, but you could play around with those priors and see what the effect is on the analysis there. Okay, so sorry this is a bit rushed, but there is more I want to talk about at the end. So the epi-CT MCMC command runs my MCMC, and what I end up with are chains that look like this. Okay, so they've converged reasonably well. You'll notice that I run this MCMC for 50,000, and I'm just showing the MCMC for the parameter estimates, not for all the rows, right? The incubation periods and the delay periods, but they are being estimated as well. Okay, so this is a high dimensional problem. The Sparks term I'm not really interested in. It's been estimated as low, which is what I want. And you can sort of see, if you look at the true value of these things, the MCMC chain is capturing it. This was 0.25, wasn't it? So, the MCMC is capturing the posterior distribution is capturing the true parameter values there. We've got our summary, just like we had before, except now I've got a posterior mean for this is my beta parameter, okay, in the SIR framework or SINR framework. My rate parameters for the incubation period and delay period. Remember, the true value was 0.25, and then I can get my credible intervals for all of those parameters. And if I was interested in the Sparks parameter, I could look at that as well as representing infection coming in from outside of the population. Okay. I can see some questions.
Yes, questions, yeah. One is on how would you incorporate the imported case from other areas into the model?
So if we're talking about in this setup here, use in terms of the data analysis and the EPI-LMCT package, we do it with the Sparks term. Okay, so the Sparks, as it stands here, allows for random infections to occur that the model otherwise doesn't explain. So that can represent infection coming in from outside. I think I'm right in saying that the package won't allow for this at the moment, but what you can also do conceptually is, multiply that Sparks term by, the number of infections that are occurring in another city. So you can tie it to an epidemic curve of another country or another city or another region.
Okay, related to the imports, instead of epsilon, why not just include the imports in the model?
Oh, you mean if you know the number of imports, you can do that, but we very rarely do. The epsilon is representing those imports. It's basically a probability that each susceptible could be infected from outside the population.
Okay. And then, okay, so now I'm gonna go chronologically. Why would someone be infected who couldn't possibly be infected? Because
okay, so remember that the MCMC is now moving around the space of the model parameters and the incubation and delay periods. Okay, so for each individual, I'm estimating an incubation and delay period. I could have a situation where everybody except one individual, I should add, so that in effect means I'm estimating the infection times and the removal times. So I could have a situation where 99 of my individuals, I've estimated their infection and removal time as occurring, by time 40. And then one person, I've estimated their infection time as occurring at time 41. Well, if the last removal time for everybody else occurred before 40, that person can't be infected anymore, and you get a 0 in the likelihood. I hope that makes sense. It comes back to the problem of the overspecification of the model. The parameters can wander around, and they can wander into situations which are completely implausible with the data. And the Sparks term allows you to sort of get back from that.
Okay, so next question. So where in the code do you incorporate the notification times, since we assume those are known?
Oh, that's a good point. So, where is it? So first off, it's over here. So the data type here is telling it that that unknown removal means it's unknown infection time and unknown removal time. We do have a situation where we assume you don't know the infection time, but you do know the removal. So that's where that terminology came from. It's basically in here, right? So the object epi, that's what I simulated back over there. So the epi that's created here when we translate the data contains all those notification times. Obviously, if this was a real data set, I'd be importing it to R and then putting it in the format that the epi object has, or the data gen object has, with the notification times.
So speaking of real data, the next question is, how would you perform model assessment when you fit your model to real data?
Okay, so generally what we do is we take a posterior predictive approach where we go through our MCMC, we sample parameter values from the MCMC, which is equivalent to sampling from the posterior, and then we simulate an epidemic. And you do that over and over again, and then you summarize those simulations in some way. usually we do it with the epidemic curve, right? So I would end up with, so here's my notification time. I would be simulating notification times, right, based on the disease model and the delay period and the incubation period model. And if I ended up with a bunch of simulations that look like this, then that's evidence that my model's not fitting this data very well, okay? If I ended up with a bunch of simulations that look like this, then, you know, things are a bit better, okay? But it's basically through simulating from the model, incorporating the parameter uncertainty we have in the posterior distribution. And you don't have to just do that with the epidemic curve. You can think of like the distribution of the final number of cases, all sorts of different ways of comparing the observed data with the realizations that your model produces.
Okay, last question for now. So this is about analogy between the deterministic in part 1 and the stochastic modeling here. So in part 1, we saw, for example, infection numbers as a smooth function of time. Would this curve be a step function here?
Yes. I mean, you can't see it on here because we've got like enough individuals, but yeah, basically these curves are moving up in steps, right? Even though, well, actually, I think these curves have been smoothed when I'm looking at them because we only had 100 individuals. So I think these curves have actually been smoothed, but really they're step functions or a step function.
Okay, yeah, thank you. Do you want to answer one more question? There's one more question.
I've just seen it. Yeah, I think it's reasonable to assume that is it reasonable to assume that? I mean, we're assuming that it has the same distributional structure, but not the same parameters, right? I mean, people will generally assume that all of these inter-event times are exponential because it's simple, but you can assume, and actually we can simulate, the package allows us to assume that they're gamma. Okay, so you can assume that there's a gamma distribution there. I've chosen to do exponential because that's what is commonly done. And no. So as it stands, it's probably best to do that in Excel. So I should read what the question is before just answering it. Yeah, the question is, does the package accept calendar dates for the notification times? So no, I would convert those in Excel before you, or however you want to convert it before that goes into the R package. Okay.
I was on mute. Yeah, thank you. Yeah.
All right. So, what have we done here? So we've done 2 analyses, essentially on the same model, right? But they're quite. One of them is relatively simple, fairly easy to do. The other one is computationally a bit nightmarish, but it's far more realistic. Right? There are things we can do sort of in between those 2 extremes, and actually we can also make the problem worse, out of which I'll talk about in a minute, and the problem is worse in COVID-19 than just not knowing the event times. So I'll talk a little bit about some of this stuff, where the research is going and needs to go, and some of the things that we can think about there for the future. Okay, so in large populations, if you're doing an SINR type analysis, the computation time can be extremely prohibitive. Okay, and now it was that analysis that I showed you at the end, I don't think it was over an hour, but it was close to an hour. Now, like I said, the package at the moment is working extremely inefficiently because it's calculating an infectivity rate for each individual, which is not necessary. But even when we've coded things up efficiently, if I wanted to model Calgary, COVID-19 in Calgary, that means 1.3 million individuals. That's going to be a nightmare, right? So what can we do? Well, there has to be a trade-off between the realism and, a trade-off between the complexity of the model and what we can handle computationally, which probably takes us back to simplifying things a bit, okay? So one simple thing is, can we assume we know infection times or removal times? Okay, like I say, there are some situations where we might know the removal times. If people are self-quarantining or animals are being cold or plants are being burnt down, then we can assume that's when that occurs is the removal time, right? Or sometimes the disease follows a very well-known path and it's not that variable between individuals. So maybe we can infer infection times from the symptoms or when the symptoms appear. If we can just assume one of those, we're halving the number of latent parameters we need to infer. So that helps us a lot. If we can assume something else like we know one or the other, the infection times or the removal times, but also assume that everybody has the same infectious period. Might be an unknown infectious period, but everybody has the same, then that removes all of the latent parameters to be inferred, right? And I just get back to the situation of needing to infer the model parameters. Okay, so we really have to think that the computation becomes a real problem in these things, and we have to think about how realistic can we make this model before it becomes computationally intractable and then useless, right? If I do an analysis of COVID-19 that takes 6 months to run, well, that might be fine after the fact, but it's not going to be any good for helping with, formulate policy or, as things are going. The other thing, of course, we can think about is doing the computation in a different way, either making it more efficient or using some sort of approximation, usually of the likelihood, that speeds up the computation. And a lot of my research is actually based around this stuff, this side of the analysis. So there's a few examples down there. So one example that's commonly used is to reparameterize your SIR or your SEIR model. Okay, so this is something that, if you want to look this up, so Pete Neal and Gareth Roberts did some work on this. I think they have a statistics and computing paper, I think, in 2005 or 6, around then. And there's a couple of other papers. But basically, they reparameterize the model to reduce the correlation between the missing data parameters. And what that does, or the latent parameters, and what that does is it enables the MCMC to explore the posterior more efficiently, so you don't have to run the chain for so long. Okay, I think that's harder to do with the individual level models, but that's one thing that you can think of. You can look at the computation itself, right? So we can compute things in parallel very easily now. Most of our laptops have multiple cores and access to large clusters. It's fairly easy, certainly in Canadian universities nowadays. So we can run what you might call embarrassingly parallel computation, where I run, my MCMC chain on 150 different cores, throw away the burn-in from each of those, and then recombine at the end, right? And that also has an advantage, and it helps me check the convergence because I can compare these chains as well. not so much with the SIR, SINR type models, but with the individual level models, the actual likelihood computation itself can be quite prohibitive because you're calculating all these infection rates for everybody, every individual. So then you can actually think about parallelizing the likelihood calculation itself. So divide the data set into different parts and send that off to different cores to speed things up, because they're all carried out at the same time, right? So it makes it quicker. With a more statistical bent, there are things like approximate Bayesian computation or emulation, which basically try to get around computing the likelihood. And the approximate Bayesian computation is probably most use with the homogeneous mixing models. The basic idea here is that instead of calculating your likelihood, you simulate a data set and compare it to your original data set in order to approximate the likelihood for some parameter value. Okay? And there are lots of flavors of ABC. There's sequential Monte Carlo and rejection and MCMC. But the basic idea is we don't calculate the likelihood. And the nice thing about this stuff is that those latent parameters just become part of the simulation. Right? I'm simulating my infection process, then I'm simulating my notification times based on that, okay? To allow me to compare some summary of that data with the original data. We can do things like machine learning classification. So we've got a few papers on this where you choose a bunch of possible generating models. So it could be the same model with different parameter values. Okay, and you simulate lots of epidemics from each, and then you train a classifier to go from the epidemic data or a summary of the epidemic data to the generating model. And then you can get really quick, rough point estimation for a new data set that you've observed. And we've only really tried it in fairly simple scenarios, but it does seem to work quite well. And I was at a talk just before Christmas, I think, where people had done this on coalescent models. So where you're modeling the evolution of the genomic sequence of the pathogen. So quite complicated models, and they've been doing a similar thing, and it seemed to be working well there. So there may be more to explore there. Or we can do really simple things like, well, data aggregation. So I can cluster my data, especially if I've got covariates on them. So instead of modeling on the individual level, I model on a cluster of individuals, and then I'd have, you know, an incubation and a delay period representing that cluster or the infection process with that cluster rather than the particular individuals. So I'm lowering the dimension. Or similarly, well, not similarly, but similar sort of idea, can we just separate our population into different components, right, and analyze those data separately? That's sort of like the, maybe via a divide and conquer method, which goes back to the parallel computation where you estimate particular subsets of your data on different cores and then try to recombine. That sort of thing probably works better in a spatial or network, or also if you can think about the spatial population, you know, if I wanted to model Calgary and Red Deer, can I really consider them as being separate populations? Because analyzing those two cities separately is going to be much easier than not. And that would seem perfectly reasonable, obviously. Okay, for those of you who don't know, Red Deer and Calgary are about an hour and a half away driving. All right. The other thing I just want to talk about before I realize I'm over time here, but I want to talk about one extra difficulty, which is quite common in infectious disease data sets, and especially in COVID-19, which is underreporting, right? So in both analyses I've shown you so far, statistical analysis, I assumed that my data set contained all the cases. Even if I didn't know when the event times happened, I assumed I knew that they did at some point. We obviously don't see that, and we don't see it in COVID-19. We have a whole bunch of asymptomatic cases. We may well have cases that are misdiagnosed. You know, early on in COVID-19, you could have gone to the doctors and they told you, oh, you got flu, go home, right? But actually you had COVID, or could even be the other way around, right? You might have COVID, so go and self-quarantine, but actually maybe you only had flu. So there may be misdiagnosis. And you also just have a whole swathe of cases that aren't reported, right? Maybe I get the disease, I live with the symptoms, I recover, I don't bother reporting. And that's going to happen a lot. Now, at least
So Rob, here,
yeah.
sorry, I want to ask that. So here you assume unbiased underreporting or allow biased underreporting?
I'm just going to talk about that in a minute.
Okay.
So yeah, so at least conceptually, the data augmentation framework can be extended to allow for, say, latent variables which represent susceptible individuals in our data actually being unobserved infections. Okay, so I can set it up so I'm essentially estimating whether a susceptible could have really been an infected individual. Okay, that results in an even higher dimensional problem and also a variable dimensional problem. Because if I've decided that a susceptible individual was actually infected, I now have to estimate an incubation and a delay period for that individual in the full SINR model, right? But we can handle it conceptually. We can use what's called reversible jump MCMC, but it increases our non-identifiability over-specification problem, and it also increases our computational problem. Okay, so you can try it, and we did do it to some extent with the foot and mouth disease epidemic, where a portion of the farms were the infection status was unknown. So we've done those sorts of analyses have been done. In COVID, if I'm modeling a city of 1 million plus people, you know, I don't think it's going to work. So a more general way of thinking about this, and this is where I'll come to Leigh's question, is to think about this in terms of a state space approach. Okay, so for those of you who are not familiar with a state space approach, you basically have a model which is modeling a hidden latent process, okay, represented by what we call a state equation. Okay, so I've written this in a very general sense, that my state xt is some function of something that happened in the past, right? Xt from the past. So for example, in this case, xt could be st, it, rt. Okay. If this was discrete time, we may be talking about a Markov process. So I'm only looking one point back in the past, but I might be looking back further. Right? I may want to look back further in the past, which is why I leave that general. But what that xt does is modeling, sort of like we saw in the first session. It's modeling the actual number of cases, the actual number of susceptibles, the actual number of removeds in the population. Okay. We then tie that latent process to the observed data, which could be the number of cases. In COVID-19, you might want to make it something like the number of hospitalizations and the number of ICUs or the number of deaths, because probably that data is more reliable, right? So Leigh mentioned before that we can have really bad bias in terms of case numbers, for example, because it depends on the number of tests that are being carried out, and we know that changes over time, and we know that changes in different jurisdictions. But anyway, we're tying the latent process, which is essentially these states up here we're trying to estimate. They're still random variables. We're tying those through some function to what we've observed, okay, which could be the cases or deaths or whatever it is. And this might be just a function of the latent x's that we don't observe, but it could be a time varying function. And in the case of COVID, we would probably want it to be a time varying function, right? Because we know that the testing regime is changing over time, etc., etc. The key to this is really having something that's reasonably low dimensional here, right? So if xt is just s, I, and r, the counts or the proportion, that's relatively low dimensional, right? So if we can keep that dimension down, this should make this thing more computationally tractable. And there are a number of people who look at this modeling in this framework. All right. I will, of course, take questions, but just let me get through these final 2 slides. You will have seen references to papers and things in the talk. I didn't get round to putting them all again at the end, but what I have done is I've listed 4 what I consider key or useful things for further reading, right? Like I said earlier, I've only really scratched the surface here. So the first thing, well, it's not first thing, it's the second thing on this list, are the 2 vignettes for the software packages, especially if you're interested in the individual level models. I would highly recommend you to take a look at the preprints that are up on archive. And like I say, in the continuous time version, the EPI-LMCT, hopefully in a week or 2, we will have a more efficient way of simulating and analyzing for the SIR models. The Keeling and Rahony book I mentioned earlier, I think it's a really nice book. It does touch on statistical aspects, but it's really about the mathematical side of the models, but I think it's a really nice introduction to that. This book actually came out in October, and October last year, and I'd missed it. I knew it was coming, and then I forgot about it. So I haven't actually read it yet, but it's one of those, you know, CRC, Chapman and Hall handbooks, which are very nice. The people who've contributed chapters to this book are top names in infectious disease modeling and infectious disease surveillance. So they'll cover, some of those chapters will cover, I assume, to a good quality, a lot of the surveillance methods that I haven't really talked about at all. And then finally, assuming people are still here, I just want to point out, this has been advertised, I think, but this is a coincidence that this is next week, but I'm on a CANSI project with these fine people down here. And as part of that CANSI project, we've run a workshop, which was originally going to be, you know, physically at Fields, but it's now an online workshop. You can still register for this. It's a research workshop, so it will be covering some things similar to what I talked about today, except in a predominantly spatial setting, but also some of the surveillance stuff as well. These are our plenary speakers. As you can see, they're extremely eminent names in their fields, and our invited speakers are very good as well. So yeah, please feel free to register for that. I should just point out, although there's an organising committee, as per usual, there's one person who does most of the work, and in this case it was Mahmood, so he should take credit for that. Okay, so I can take, sorry for overrunning, I hope some of you are still here, and I can take any questions.
Yes, Rob, yeah, there's still 116 participants right now.
Oh, yeah.
So yeah, we do have a question more like a comment. Does access to healthcare make it difficult to compare case numbers in Canada versus US, for example?
Well, depends what you're trying to compare, I suppose. If you're trying to compare health systems, maybe that is what you want to do. Obviously, I mean, the big, oh, I see, you're probably talking about the testing regime. So yes, the fact that the testing rates are very different in different places and at different times does make it very difficult to compare. Also, we have to think about the size of countries, right? Comparing the US to Canada, just in terms of number of cases, doesn't seem very fair. So you want to think about the case rate and the mortality rate and those sorts of things.
Okay, so right now there's no more questions, but before everybody leave, Rob, can people still register after today? Just to, you know, I have a sense that somebody got a hold of the link and participate in the workshop, but they actually not in your system for the follow-up communication. So how would you want to proceed from here?
You're talking about the fields workshop?
No, for this today's workshop. So, for example, I don't know if you would like to collect some input regarding the workshop itself, and then some other kind of follow-up communication. So, but to do that, I guess you have a list of the people who registered, but today probably somebody.
Yes, so I have an up-to-date list of the participants. So yeah, anybody who came in late, I just forwarded the link because I thought it was going to be easier.
Okay.
But yeah, I can send that to you.
Yeah. Okay. So any other questions or suggestions? And I guess at a certain point we'll do a kind of survey on the workshop itself, and for people who are interested in COVID-19 epidemic modeling, I guess as a biostat section, we can also talk about how do we gather forces and to proceed the research. Yeah,
that is a good idea. I mean, I have to say, at the moment, I'm sitting here thinking this went okay, and a survey could ruin that preconception. But yes, no, this is a good idea.
Yeah. Okay. So any other comments or questions? Okay, so if not, Robert, thank you so much. You know, it's a wonderful workshop. I really enjoyed it. And everybody, so if you can, give a round of virtual applause or hands up, and whatever we can do, and enjoy the weekend.
Thank you very much.
Thank you.
Thanks all for attending.
Thank you. So Patrick, Robert, maybe we stay a bit after.
Well, we could do, but then we'd have to wait for all the attendees to leave. I guess I could boot them all off.
If you want to chat, I can just I can set up another Zoom meeting and just invite you.
Yeah, why don't you do that? Sure.
Okay.
Many of us can, but yeah.
I'll do that now then. Okay.
Okay, great. Thank you. Bye, everyone. Yeah, bye.